a couple definitions here. So ML, is the science, maybe a little bit of the art of programming computers so they can learn from data. So here's some more general and more engineering focused definitions, right? So Arthur Samuel, 1959, gave the definition that, ML is the field of study that gives computers the ability to learn the ability to learn without being explicitly programmed. Right, so the goal there is that because we don't have to explicitly program the machine to do a task, but rather we train the machine how to do a task, the machine can go out and do that task over and over and over and over again. So that's pretty good. 1959, that is a long time ago, right? That is before modern computers. But people have been thinking about this for a long way. So 1997, so let's go 1959, 1997, so a much more recent one. A computer program is said to learn from experience E with respect to task T and some performance measure P. Right, so that's Tom Mitchell. And then if you can measure its performance P on a task T, you can work your way back to improve the experience E. That's kind of a more mathematical way to frame it, right? And so that's what we're going to try to do. We're going to try to define the task, define the experience, and define the performance. So we will use two common variables to do this, right? We're going to use X and we're going to use Y. So you might have like a lowercase x of I is a vector of all feature values. For an ith instance. And at that same moment, yi is its label. the desired for the instance. Right, so here what we're looking at, a good way to think about this at a very conceptual scale is X is your input and Y is your output. And then I is your instance, right? So let's say if I'm buying and selling houses, I might have a specific house that I'm selling, I, and then I might have a number of features for that house, the size of the lot, the size of the house, the number of bedrooms, the number of bathrooms, right? The more bedrooms and bathrooms, the more expensive the house. And then Y would be the cost of your house, because that's typically what you're trying to predict, right? So Y would be, and then the Y of that Y of I would be the cost for that specific house, because you might have 100 houses in your data set. Each house might have 20 features. So your X would be 100 by 20, and then your I would be 100 by 1, because you just have one cost per house. So a general definition that's pretty good is ML algorithms are described as learning a target function F that best maps Y of F of X, right? Oh, sorry. That best maps X, the input variable is X, onto the output variable Y. And so mathematically, we can just write that as Y equals some function that we're trying to define of X, where X is our input, Y is our output, and then the function is what we're trying to learn. So all we're trying to do in this class is learn the F of X. So that's described as a standard learning challenge, and the goal is to predict future values of Y using new samples or variables of X. So the function F that relates inputs to outputs is not known, and that's what we're trying to learn. However, we're never going to have anything that's this clean, right? Typically what we're going to have is some sort of error associated with the problem. So we're typically going to have a model that looks something like this. Our output Y is equal to our function F that we're trying to learn of our input data X plus our error, some error value, right? And as long as we can understand some of the error value, then we can go ahead and do that. Now the question becomes, how do we create that model, right? And so we're going to create that model through training. Which is a compute intensive process. So create, let's say, training creates F as a compute intensive process. And then we have inference. And that's using the model and that can be computationally cheap and is often performed at the edge, right? So when we talk about training models, it's very expensive. and then running the inference through a model can be quite cheap.